Alright, electric cells. Cells. To make a chemical cell or a battery, you can begin with a container of weak acid, 2 electrodes made of different materials. So if you're making a lemon battery, you've got to use 2 different types of electrodes, a cathode and an anode. Different metals dissolve in acids at different rates. When metal dissolves, it enters the acid as a positive ion, leaving behind an electron. We call the weak acid the electrolyte. We call the least negative metal the positive terminal. We call the most negative metal the negative terminal. Okay. The big thing to pull away from all of this information, we have the least negative metal is the positive terminal, and the most negative is the negative terminal. And a battery is composed of these cells. Often there are multiple cells. All right, so we put one metal into a weak acid, put another type of metal into a weak acid, and you'll see how the charges spread out here. So now we have the electrolyte, and we now have a positively charged side over here and a negatively charged side over here. Think of chemical cell as a device that converts chemical energy into electrical energy. If we connect conductors and a light bulb to the positive and the negative terminals, we see the electrons begin to flow. We see the electrons begin to flow in an electric current. Why do the electrons run from the negative to the positive in the external circuit instead of the reverse? All right, so they're going from the negative to the positive. This is the electron flow. We've already talked about this. Okay, so electrons are running away from other electrons because likes repel, so they're being repelled towards the lesser of the negatively charged terminals. Holy cow, sorry. Whew. Alright, so we've got a light bulb, a switch, nothing's happening, and then when you close the switch, then you'll start to see the electrons go through and the light bulb will light up. Each time an electron leaves the negative terminal, the acid creates another electron. Creates, bad word, but it's fine. Each time an electron enters the positive terminal, the acid neutralizes the electron. This process is maintained until one of the metals or the electrolyte is completely used up, a dead battery. A primary cell can't be recharged, but a secondary cell can be recharged by applying an external voltage, reversing the chemical reaction. So any of those rechargeable batteries, they have to have multiple cells in them. There's one primary and there may be one secondary or 2 secondary, however many extra cells that can be recharged. Alright, so we've got the Duracell with a positive terminal, this little nub at the top. The negative terminal is down here. Then we have this old cell phone battery where we have the positive terminal on the right side and the negative terminal here. It's always the same thing. So a current isn't really just one electron moving through a circuit. In reality, it's like a chain of them, each one shoving the next one through the circuit. Recall the charge law. Like charges repel and unlike charges attract. Explain why the current flows from negative to positive in terms of force of repulsion. Consider electrons at A and B. Both electrons feel a repulsive force at their respective electrodes. Here you go, you see their repulsion happening going through here. This is called electron flow. This is not how we handle dealing with circuits. We're looking at electron flow just to see how these batteries work. There's A and B, sorry. A's is bigger than B's because there are more negatives repelling at A than B. So A wins and the electrons run away from A and they go towards B. Consider electrons at point A and B. Which one has more potential energy? Go ahead, pause, think about it. Again, this is going to be B and this will be A over here. So the electron at B already has gone through the circuit and is returning to the cell, so it can't do any more work. It's used up all of its energy. It's given away that piece of candy that it got from the battery. The electron at A still has the full circuit to travel, and so can still do work on the bulb and transform allow that light bulb to transform some of that energy that it gets from the charge. So the electron at A has more potential energy. Back in the days of Ben Franklin, going back to conventional current again, just as a refresher, scientists understood that there were two types of electricity, positive and negative. What they didn't know was which one was actually free to travel through a circuit. So Ben Franklin guessed wrongly that it was the positive charge that was flowing through the circuit. So his vision of chemical cell looked like the one on this slide. Positive charge flow is called conventional current and is still used in circuit analysis. So what Ben Franklin was thinking was we had the protons, the positive charges, being repelled and going towards the less positive side. This is the conventional current. Remember, we're only using conventional current when we look at circuits, not electron flow. Now, electric potential difference. We've defined electric potential difference as the amount of work done in moving a positive charge Q from some point of a lower potential energy to a point of higher potential energy. Remember back in the last lesson, it was that pump that took the water from the below the ground and brought it back up to the top of the reservoir. The units for electric potential difference are volts and can be seen from the formula joules per coulomb. So potential difference equals the change in energy per charge, or work, capital W, over Q. Electric potential difference is often abbreviated as PD. Think of a battery as an engine that uses chemical energy to take positive charges and move them from low potential to high potential inside of the cell, so that they can only do work outside of the cell in the external circuit. So no work is being done inside of the battery. It's just there's that bringing up of the charge from the low potential to the high potential, right? If we think about the river, high potential to the low potential over here at the elbow. The schematic for the symbol is a switch as shown. Low potential to the high potential. So once the charge goes all the way through the circuit, how does it get back here? Well, that's the magic that's happening inside of the battery. We've got this chemical energy that it's going through, and it's... Oh, that's bad formatting. Nuts. It's okay, we can still see what's happening. So we have the battery right here, the cell right here in the schematic, and then the charge will go through the lamp and then go to the switch and then come back to the negative terminal, the lower potential energy. As an analogy to gravitational potential energy, think of the chemical cell as an elevator powered by a chemical engine. Inside the cell, the positive charges are at low potential and they're raised through chemical energy to a higher potential. Once they get outside of the cell, positive charges at high potential are released to the circuit to do their electrical work, losing the energy as they go.